Start with another example in this lecture. 15th lecture number 15 to find the GCD of two number. After completion of this example, when you listen the previous lecture, when you watch the previous lecture, you can easily observe that the procedure for finding the GCD of two number. Okay, here we give another example because your note contain this example. You have to realize the procedure for finding the finding the GCD of these two number. Exactly for that reason, here we given another example to finding the GCD. Find two integer u and v satisfying 1 equals to 63u plus 55. It's a very easy, very interesting example for you, because here it is not mentioned that the GCD of 63 and 55 is 1, but still the question, according to this question, you can easily observe that the GCD of these two number is 1, because the procedure for using to find the GCD of any two number is the linear combination of these two numbers in the form of AU plus BV. Exactly for that reason, here we mention these particular things. 1 equals to 63u plus 55b. So when we want to find this particular solution of this particular result, in that case you have to find GCD of these two number, which is 1, and exactly the same procedure follows in the previous lecture as well as this lecture. 63 is equals to 1 into 55 plus of 8. Okay, when you divide 63 by 55, it's a very easy procedure, because 63, when you divide 63 by 55, again we mention this one, when you divide 63 by 55, we consider there is 1, the result becomes this one, 55. The remaining result should be 8. The next step to find the GCD is you have to divide 55 by 8. So the result becomes 648. So it's becomes 7. When you divide 7 by 8, exactly the result is here, it should be 1. The result is 7. The remaining is 1, and we divide 1 by 7, so it should be 1 to 7. So the GCD should be 1. The last non-negative remainder, the last remainder should be the GCD. So the GCD of 63 and 55 is 1. Exactly this procedure is written in this particular manner. You can easily observe 63 is equals to 1 into 55 plus 8. 55, when divide 55 by 8, that should be 6 into 8. 6 into 8 plus 7. When we divide 8 by 7, that is 1 into 7. 1 into 7 plus 1, and that's all. Okay, so here it's the way of representation. 1 should be written as 8 minus 1 into 7. 8 minus 1 into 7. Next we put the value of 7 in this particular result. The 7 can be written as 55 minus 1 into 6 into 8 minus 6 into 8. So here we write this one, and after calculation the result becomes this. Next we have to put the value of the previous remainder, which is 8. So here we put the value of the remainder. 8 is can be represented as 63 minus 1 into 55. So here we write 63 minus 1 into 55, and after the arrangement of these, the result becomes this. So here we can find the solution where u is become 7, and b is becomes -8. So the result u is 7 and b is -8. That is a procedure. You can evaluate the GCD as well as if the equation is given in that particular form, you can find the value of the corresponding variable. And the question is that we have already mentioned that this equation is not the unique solution, because the rank of this is a system. If we consider this is a equation with two variable u and v, okay, two variable u and v, so here the number of solution should be infinite, because the rank of the coefficient matrix is 1, rank of the augmented matrix is 1, therefore the number of solution of this equation is infinite. Here we can find the number of integer solution. Here we can find the number of integer solution. They may be 1, maybe 2, maybe 3. That's totally depend upon the problem. Okay, so next we move a very important theorem regarding this particular chapter is this one. You can also find two integer u and v. That is another example. Sorry, that is another example. This one, it's also very interesting for you. 54 into u, just resolve this one. 24 into v. In the previous example, here we mentioned that the number the GCD of these two numbers should be here 1, but here the GCD of two number 54 and 24, that should not be 1 or that should not be equals to 30. So first we have to calculate the GCD of these two number, that should be divisible by 30. This GCD should be a divisor of 30, because first we use the division algorithm. 54 is the largest number regarding to the 24. Exactly for that reason here we divide 54 by 24. The division algorithm says that should be 2 into 24 plus of 6, and next we have to divide 24 by 6. So 24 is equals to 4 into 6. So it's proved that the GCD of 24 and 54 should be 6. That means according to the theorem of the expression can be represented as the GCD's form is AU plus BB. So exactly for that reason 6 can be written as 54 from this equation. 54 minus 2 into 24. The question is how can I find this equation? The right hand side is 30, here it's 6. So how can I find how can I reduce this 6 to 30? Just you multiply it by 5, and when you multiply it by 5, the result becomes 5 into 54 minus 2 into 5, that is minus 10 into 24. So it's the exact equation which is given in your question. Therefore the value of u becomes 5 and the value of v becomes 10. It's a very easy procedure. Sometimes the GCD is given in the right hand side, sometimes the right hand side should be a multiple of GCD of the given number in the form of u plus of bv. In that case we can use this procedure to find the result. So that is a very important theorem for your syllabus regarding examination and others thing. It says that if k be a positive integer, it's very important, k be a positive integer, and GCD of kb should be written as k into GCD of a comma b. It's very important. It's the term regarding the positive integer. If k be a positive integer, again we mentioned k be a positive integer, then the GCD of k plus kb, that should be equals to k into GCD of a comma b. Why we use this positive term? Before we explain the proof of this result, you have to explain the application of this result, where the most of the student make a mistake. Exactly for that reason here we give an example. Say you just find the GCD of 10 and 15. Okay, GCD of 10 and 15. Clear? So the result becomes this. That should be equals to 5. Okay, But if we do not multiply this number by a positive integer, say we just consider the multiplication by a negative number, what happens? Should realize this. If we multiply 10 and 15 by minus 2, the result becomes minus 20 and minus 30. The GCD is should not be a negative number, it should be the greatest common divisor. So the GCD is of these two number should be equals to 2 into 10 into the GCD of GCD of 10, 15. That means you can use this result. You can also use this result if k should not be a positive integer. You can use this result as a mod of GCD of a comma b. Okay, clear? So here is the theorem. If k is a positive integer, then GCD of k kb is this only k GCD of a comma b. If k is not a positive integer, that means if k is any integer, then you should take here the mod of k. Okay, then you can easily recognize this theorem. So it's a proof of this theorem. First we consider D is the GCD of A comma B. Proof is very easy. D equals to U plus BB. We have already mentioned D is a divisor of A, D is a divisor of B. If we multiply both sides by K, this one, okay, and KD is a common divisor of K and KB. It's very important. Next you have to prove that KD, if KD is the common divisor, if you can prove that this KD is the greatest common divisor of K and KB, KA and KB, then you can easily observe this result. And how can I prove that this result is the greatest common divisor? If we consider C is any common divisor of K and KB, if you can prove that this C should be a divisor of the common divisor, greatest common divisor KD and KD, then we can say that KD is the greatest common divisor. Okay, so exactly for that reason here we consider C is a common divisor of K and KB. Okay, since C is a common divisor of K and KB, therefore C should divide K, and then K should be written as some constant into C, and K is also divisor of KB, C is also divisor of KB, so KB should be written as KB into C, therefore KD, here we use KD and D is replaced by AU plus BB, and if we replace this one as exactly in that form, the result becomes this, which is proof that KD is equals to some integer into C. Okay, some integer into C. Since it represents some integer into C, which proves that C is a divisor of KD, that means if we consider C is any common divisor of K and KB, then C should be a C. If we consider C is the common divisor of K and KB, then you can easily observe that K is also a divisor of KD. That means KD should be the greatest common divisor. That means KD should be the greatest common divisor of this number. Consequently, KD is the GCD of K and KB, which proves the result. And that's all for this lecture.